Good afternoon and welcome. My name is Ashley Naranjo, and I am an educator here at the Smithsonian Center for Learning and Digital Access. This is the second of 3 online sessions this spring 2016, created to support Smithsonian Learning Lab workshops for middle school teachers in Allegheny County, Pennsylvania. It's funded by the Grable Foundation and in partnership with the Allegheny Intermediate Unit and the Senator John Heinz History Center, which is a Smithsonian affiliate museum in Pittsburgh, Pennsylvania. This session will be led by one of my colleagues here at the Smithsonian from the National Air and Space Museum in Washington, D.C. Dr. Williams has taught at the university level and has also created many of the experiential learning stations at the museum. We'll think of our time over the next 45 minutes as kind of a 101 introduction to the content. We'll answer questions such as what is remote sensing and talk about the fundamentals of image interpretation. We'll leave you with a few classroom-ready examples that you can share with your students, as well as a much more extensive list of resources to continue your study of satellite images. I think you'll find that this medium allows for the investigation of change in a location over time, but also has several connections to other disciplines in addition to its deep roots in geography. This session will be interactive, so please feel free to ask questions. You can enable the Q&A app on the right-hand side of your screen. Just click the 3x3 grid, and then you should see the option for the Q&A app in blue. Without further ado, I'd like to turn it over to my colleague, Stephen Williams.
Hi, good afternoon, everyone. It's a pleasure to be here, and I'm looking forward to sharing the next little bit with you and talking about remote sensing and its many applications. So good afternoon. First of all, let's talk a little bit about what remote sensing is, since that was what it was built. I mean, we're used to dealing remotely with our surroundings anytime we're not actually physically in contact with it. Our eyes are very good at doing that, and we look out and use our eyes in a way we don't normally just think a lot about because it's second nature to understand the world around us. And as our technology has improved over the millennia, we actually have mechanical, optical, and other aids to help our vision and our senses do a better job of informing us more completely of our surroundings. Next slide, please. Now, I happen to be sitting just a few hundred yards from a very important spot in American history where just over 150 years ago, a fellow by the name of Thaddeus Lowe demonstrated to President Lincoln the enormous value militarily of having a high ground perspective to look at movement of troops, artillery, and troop emplacements and so forth, just right here on the National Mall over 150 years ago. And if you think about it, having that high ground perspective allows you to see just the same way you always do, but from a different perspective. If you've ever been out in the fall to a place that has a corn maze, invariably there's a tower nearby where people with sharp tongues can watch you make your way through the maze and provide assistance or lack thereof, because they can see the whole pattern. You can't. You're down in the cornfield. You can't see the forest for the trees or the path out for the corn stalks. So that extra high ground perspective is very valuable. And what better high ground perspective is there than the highest of high grounds, or Earth orbit, looking down below at all the things going on? Next slide. Now, because we're going to be using our eyes, even if we aid them mechanically, we have to understand the limitations that our vision system places on this. Now, space is filled with electromagnetic radiation of all wavelengths. The visible part of the spectrum, that which we can see as the rainbow when we pass it Pink Floydly through the prism here, is just a very, very small part of the overall spectrum. You can see from the numbers on there, this is a very logarithmic scale, so it's covering a very wide range. Shorter wavelengths than our eye can see, the gamma and X-rays and ultraviolet, have valuable information, but without mechanical assistance we can't see them. Similarly, the infrared, microwave, and out into radio wavelengths are much longer than our eyes can see. And there's information there too that we can't begin to see. So by understanding those limitations and using mechanics and optics to take information from these wavelengths we can't see and put it into wavelengths our eyes and brain can handle is a very powerful way of extending the capabilities of our vision. Similarly, we'll also want to expand how small an object we can see, okay? And while our eye is really good at telling nuances between colors, we have instrumentation that can do that better as well. So that's going to be the basic tool that we use. Next slide, please. Now, in the olden days, we had the capability to send objects into space and observe the Earth from above, but we had no way of sending the information back here to Earth. This was back in the film camera days. We even resorted to tactics like developing film on board the spacecraft and kicking it out and parachuting it back to Earth, that kind of thing. But today, it's all done digitally. We have a digital camera, much like your video or regular cameras today, just a little more high-powered, and it takes a digital image and radios that back from Earth to Earth from space, or from wherever the camera was. And then we do three things to it, the three things that are shown in this slide. First of all, there can be errors made during the acquisition and transmission of the image. And there are mathematical ways we can identify those things. If you've seen an original NASA picture, it has a salt and pepper texture to it. Some of the little picture elements or squares of the picture are all dark, some of them are all white. You can do things mathematically to make those like their neighbors and take that away and restore the image to what it should have looked like before those errors happened. And then because it's digital, you can actually do the same things we used to do in the olden days with the contrast and brightness knobs on a TV with a tube in it. By changing the settings, you could enhance or suppress the contrast. You can make everything a little bit brighter, make everything a little darker. We can do that too with the image digitally, and that gives us more information than we would otherwise have. And because it's digital, and because we can add other data sources on, we can actually get more information out of that image than we could just by old-fashioned, by eyeball analysis alone. I have behind me a wall map that you might have in your classroom. It's low-tech, but it is an image representation of the Earth to which ancillary information has been added. Cities, roads, political boundaries, elevation information color-coded into it. All of those things augment the image in terms of the information it can carry and convey to you. And digital technology allows a more advanced version of that. Next, please. What we're doing, though, when we have that image, has a lot of correspondence with what we look at when we're trying to analyze art. I did a discovery station for the museum called What Are You Looking At? What are you looking at? That would have caused a problem. And one of our best teams at performing that particular station had a scientist and a fine arts graduate together, and they both approached image interpretation from a different perspective, but through the same parameters. Some of these are pretty self-explanatory. For example, the first two, size and shape of an object that we see on an image. Can you think of any sizes or shapes that are alone distinctive enough to tell you what it is you're looking at without doing any other analysis? I'll bet you can, especially if you're in the DC area. Go ahead and type them up. I'll watch them as they come in and react to them. But I'll get you started with one of the most obvious, and that is the military headquarters building just up the road a piece. Its very name gives away its shape distinctive enough to identify it, especially from above. Of course, I'm talking about the Pentagon. And there are other distinctive shape, words that are used to describe geographical or man-made objects, where that gives it away. And another example would be a cloverleaf interchange. That'll give a way of just what it is. The White House is another. Thank you, Tess, for chiming in with that. There you have a distinctive shape and a distinctive color, and that gets us to the third parameter, tone, and then texture relates to that as well. In a black and white image, tone is how great it is. The Washington Monument and Capitol buildings are also excellent examples of where shape chime in. Thank you for the input. Now, if you're looking at, for example, a forest, again, it's hard to distinguish the individual trees because the forest is in the way, and if you're just looking at the tree canopy, you're not seeing individual objects, and there's a variation in tone across that object, the tree canopy, that you can't tie to individual trees. But it has a distinctive modeling of that tone that we would call texture, and that can be distinctive in a way. Also, keeping with things like trees, pattern comes into account to help you identify at least certain kinds of trees that are in certain places, especially if people are helping. I'm sure you can think of a distinctive pattern involving trees, and perhaps next time you're munching on an apple or an orange, something like that, because orchards are planted by people in regular rows that are a dead giveaway when seen from above. The Washington Monument that Kate mentioned earlier, if seen from the side on a sunny day, will cast a shadow that reveals its shape. Sometimes you can identify a bridge from above. You can identify the bridge structure. You can't see it directly from above, but if the sun's shining from the side, you can see its shadow and tell whether it's an arch bridge or suspension bridge, a truss bridge, all the various kinds. And you can even, if you know the time of day and the day of the month, you can determine the height of objects from their shadow, or reverse that. If you know how tall the object is and you can measure the shadow length, you can determine what day of the year it was or what time of day it was, not uniquely, if you have that other information. The last two help you in this problem solving. Certain things appear on hilltops or other locations, so if you're looking at a hilltop and you see something you might be having a hard time identifying, a water tower or an observatory, that sight of that object will help you. And sometimes you can't identify objects but for the object they're next to. A large-scale reservoir with a dam is likely to have hydroelectric generation and transmission equipment. If you saw the transformer yard by itself, you might not be able to tell what it is. But it's not by itself. It's next to a dam. Bingo. That gives you some extra interpretability. So it's like a big treasure hunt or a big puzzle that you're trying to solve using this high ground perspective, and these 8 tactics, alone or in combination, can give you just what you need to see. Let me give you a little fuller example on the next slide here. I mentioned tone before. This is 2 images. The left-hand side is in visual light, and the right-hand side is in it's false color infrared, it's called. What you see isn't the real colors. It's of the Salton Sea and Imperial Valley in southernmost California. Now, a lot of the video screens, especially in the tube days, had 3 electron guns and 3 phosphors, red, green, and blue. And we can fool our eyes into seeing full color if we present our eye with a red, a blue, green, and a blue image simultaneously. And as long as we're putting the red camera into the red phosphors, the green camera into the green, and the blue, you'll see something that's relatively true colored. But you don't have to do that, especially when you have sensors like Landsat, which produce this, that can see outside of the range of normal vision. For example, if we take near-infrared light, just a little bit longer than the light we can see, and put it into the red image, so our eyes see on the picture red where it really is infrared. We can get a visual image we can see that is different than what our eyes would normally produce, and that's what the one on the right is. Turns out that chlorophyll not only is very reflective in the green part of the spectrum, that's why plants are green, it's also extremely reflective in the near infrared. This technology was originally developed in World War II as camouflage detection. Green paint did really, really well, but most green paints are dark, non-reflective in the near infrared. So if you have a camera that can take pictures in the near infrared and portray that as red, objects with chlorophyll will stand out bright red, whereas objects with green paint will appear dark. So what you're seeing here is agricultural activity in the Imperial Valley, and the redder the image, the more green chlorophyll is present in that particular area. We'll return to this Salton Sea region at the end of the talk as time permits and look at this phenomena in a little bit more detail. But it's not just what the tone is, it's also the quantity of data that you have to work with. Next slide, please. Here I've taken an image, an air photo image of Meteor Crater in Arizona. The best view is in the lower right. You can see that the crater is slightly squarish in shape. That's because of the structure in the underlying sedimentary rocks. But the object on the left, about 9:30, if it were a clock face, is the visitor center, and you can see the road winding down to it. That's a 2-lane highway. This object's about 3/4 of a mile across. I give you a sense of scale, and its depth is greater than the Washington Monument is tall. It's the youngest, freshest, larger impact crater on Earth, but compared to the ones we see elsewhere in the solar system, it's tiny. The bigger, older craters have been erased by geological processes on Earth that don't operate, at least don't operate at those speeds on the Moon and elsewhere. Now, I've artificially degraded the image all the way down to the upper left, and if we think of data as having a cost associated with it, it's important to figure out how little data we can get by with to make the interpretation we want to make. Depending on the question I ask about this particular object, you may or may not need the expensive high-resolution image in the lower right. You probably can't do much of anything with the lower left, but how good is good enough, and how much does that cost become an important part of the equation. Next, please. Another bugaboo, especially looking at Earth from higher altitude, is that our atmosphere is not uniformly transparent to different wavelengths. Our eyes evolved to see visible light, and that's one of the zones on the spectrum that gets through the atmosphere relatively unscathed. This is a blockage diagram, so the blue parts are the wavelengths where the atmosphere is opaque, and the ones where the line gets up near the top of that are wavelengths that the atmosphere is relatively transparent to. So we have some fundamental limitations that looking at Earth imposes upon us, that say looking at with spacecraft at other planets, at least the smaller ones that don't have atmospheres, have to deal with. Next, please. Now, so far I've been thinking about using the Big 8 to interpret what it is we're seeing when you're just dealing with a natural object. And it's up to us to utilize those 8 elements of image interpretation effectively to figure out what it is you're looking at and what it's made of. But if there's somebody at that end who doesn't want you to do that, there are 3 tactics they can do to interfere with your interpretation of that area, and those are concealment, camouflage, and deception. Next, please. If you've got a relatively small object, a building, a train, you can actually cover it up so that you can't see it. You put a roof over something, somebody above it isn't going to be able to see it anymore. They'll see the roof, but they won't know what's underneath it. And here's some examples of a railroad train in Burma that was at least partially concealed, distinctive shaped building in Pilsen, Czech Republic, the lower right, that's had the distinctive building patterns concealed by nets. Another one there at the top on Saipan. So if it's small, you can keep the interpreter from seeing it. Next, please. But if the object is too large, you might need to still fake them out, but you have to hide it in plain sight. And that means you use things like pattern or tone or texture to interfere, not aid, the interpretation process. The upper left is an airfield that was built in an orchard, a palm tree coconut grove, and over time, as they had to clear some of the trees, they kept up the illusion of the pattern to help conceal by painting green spots on the growing runway. The aircraft manufacturing plant in the lower right had very distinctive shaped roof buildings. You can see they were pretty limited in their ability to use a checkerboard or pattern to resemble smaller buildings to break up that pattern to keep you from interpreting that image. So this was a little less effective, but you can get an idea from the attempt. Next slide. Lastly, if you've got something really big, like a armament works or an oil refinery, you can't hide it, you can't really camouflage it, so you build out some fake ones all around there and hope there's safety in numbers, kind of the fish in schools philosophy. This is a place called Skoda in the now Czech Republic. Some of our DC Metro cars are made in what used to be a World War II armaments plant. And of course, Pilsen is quite famous for other products these days other than war material. Next, please. Pilsner beer, in case you didn't catch it. All right, here's an example of one of the finest bits of camouflage. You wouldn't think that they could get away camouflaging something the size of a battleship in this image, but take a good close look at this. A battleship is significantly larger than the two ships underneath the words "Find the Battleship" at the top. Okay, that's a hint. And it's not going to be in the middle of dry land, well, or at least what looks like dry land. There's another hint. So take a look at that, and if you've got a guess, go ahead and type that in. I'll give you a second before I can't contain myself any longer and spill the beans.
So if anyone has any guesses, you can use the Q&A app, which is in the top right. You can hover over the 3x3 grid and then go ahead and share a guess with us. It looks like Linda's
bottom center. Yes, Linda, you're absolutely right. There's a kind of a square-shaped inlet, bottom center. There is a series of 4 boats. The cursor now is moving right to it. Okay, what they've done is they've altered the distinctive shape of the bow and stern by adding a floating addition. The bow is right where the arrow is there. The stern is on down, down, down. You've got it. Oh, this is great teamwork here. The superstructure of the ship and the armament are darkened so that they're not as obvious. If the sun weren't low, we're probably looking south, the shadows would be even less advantageous to the interpreter, and it would appear a little washed out. You can see some of the buildings are accentuated throughout the image because they're casting a fairly strong shadow downward. The same is true for the bridge superstructure on the battleship. But if you were in a high-altitude aircraft moving fast with anti-aircraft fire around you, you might have a hard time identifying this thing without the comfort of looking at a photograph in the office in a rear area. So that gives you a rough idea. Sorry for the militaristic components on the prevention, but this gives you at least a little idea of some of the basics of image interpretation. What I'd like to do next is next slide is to talk a little bit about some applications a little closer at home. I know you're interested in geography, history, archaeology, things like that. And one of the things that remote sensing is particularly good for when you're looking at Earth from space is it's just like that tower in the corn maze. You can see a lot of the big picture from a high ground perspective. But you also need to have what's called ground truth. You can get a pretty good idea of what's going on by looking at it from space, but until you actually go there, you're not 100% certain. And a lot of what people who do this for a living do is they look at all kinds of features and visit representative examples. You can even take it to an additional extreme by looking at places on other planets, comparing them to Earth that way, and then a compare and contrast type activity that's near and dear to all of our educators' hearts. Next slide. Some of the ground truth that gets at information that can be dealt with remote sensing deals with changes with time, and I know that's an important thing for the geographers and other teachers amongst us. In some cases, the changes are radical and abrupt. Here in the space of just over 60 years, a human lifetime, an entire glacier has retreated, several miles. This is an enormously rapid change, and there's lots of things like that associated with climate. Next slide. Either from the ground, or over time from air photos, or next, if you're looking at things from space, I mentioned the Salton Sea in California drying up. This is the Aral Sea in the former Soviet Union, and it's suffering a catastrophic drying out. It's a big chunk of it is almost gone, and this obviously will have biological, ecological, geographical ramifications, and we'll get to touch on dried lakes when we return back to thinking about the Salton Sea. You can also look at before and after with some of that information extraction phase in mind. Next slide. One of the things that we are increasingly concerned about as we look at the Earth from space is the state of the jungled regions, the very densely vegetated parts of the world that produce a lot of the carbon dioxide removing capability that plants provide, freshening air, converting carbon dioxide into oxygen. But these are also valuable agricultural resources. This particular one's in Bolivia. And the rate at which the native vegetation is being disrupted for short-term agriculture, these are not very strong soils, so they have to be husbanded very carefully for sustainability. If that doesn't happen, the ground loses its capability to support literally life-giving trees and vegetation. You have two photographs here, one from 2002, the middle one on the left, one from 2008. In the space of 6 years, there's been a lot of change. But those fields are pretty small, and unless I can overlay the images or somehow get them to where I can really focus in and compare them, it's hard to put any kind of quantitative measure of how much change has taken place. And that's where information extraction and the beauty of this being digital data comes into play. Because these are digital images, they have a number associated with them in each of the color frames. You have an X and Y coordinate like a checkerboard, and each of the checkerboard squares has a color value. And you can tell the computer to look for a square that in the earlier image is green, and that same geographical square in the later image is brown. And you can tell it every time you find a square, a pixel element that looks like that, color it red. Or color code it by the difference in greenness and brown. Something that was extremely green and extremely brown, color that bright red. If they're closer together, sort of green and sort of brown, maybe make that a warm orange and so forth. Then you can color code these things so that your eye can see them much better. The bottom left image is a change image that shows where brown or green went to brown. And on the right, it's split into more color groups to give you a little bit more of a nuanced, detailed look at these things. Now you're using the color discerning capability of the eye to understand what's going on in greater detail than even if you were looking at the images with just your eyes alone. Next, please. Now, like the map behind me, we've got image data, and you can add data to that, okay? Elevation data, details on colors, and so forth. And you can look at it in different times. On the right, Yellowstone is shown in 1989 and 2008, all right? There was a big fire in Yellowstone in '88. The lower image shows a lot of brown areas. That's fire damage. But it also cleared out a lot of literally dead wood, all right, and undergrowth and so forth, so that the first plants to repopulate the burned area would do pretty well, and there would be a steady progression up until the climax forest is back restored again. And we're catching it at 2008 as that's going on, and you can see the intensely red zones map closely to the burn zones. The places you're getting the strongest, most chlorophyll-rich growth is in the area where the existing vegetation was removed by fire. As time goes on, you'll get a more even tone. It'll start looking like, if we had an image here from '87, it'd be mostly green, and that's what it probably looks like today, another 8 years after the upper image. On the left is the island of Madagascar, which is in ecological difficulties because of non-sustainable land use practices. And there's an enormous amount of soil erosion taking place. The topsoil is being stripped, and Madagascar can only support both native and agricultural vegetation to a significantly smaller degree than it did in the past. And you can see some plumes staining the water around the island of sediments of different colors. The one circled by the hand from on high is a really good example of that. That probably has some algae in it as well, and we're actually seeing the chlorophyll in that particular case. Nutrients are being washed off from the land, causing an algal bloom. If that happens in a lake, all kinds of bad things can happen. It kills the fish, it removes the oxygen from the air, and so forth. But it's not doing their coastal ecology a whole lot of good either. So we can keep track of time, we can keep track of changes with time, and look at these data sets to get a lot more information that way. Next, please. I'll only show a couple of these because there's hundreds of them. We've put up a whole constellation of satellites to look at the Earth and look for very specific colors, patterns, and so forth for specific analyses. This one is a device that's very sensitive to various pollutants in the lower part of the Earth's atmosphere, the troposphere. You're talking several hundred parts per billion, so that's not a whole lot, but that can be a lot if the stuff is particularly nasty. And this is looking at carbon monoxide, and you can see some examples that, at least in South America, in large part are coming from large-scale burning of vegetation. The reddish spot in China is they're using a lot of coal. There was some, you can see there's some crosstalk between Africa, Southern Africa and South America. So there's a lot going on in here to understand. Next, please. Another mission that's designed to look at rainfall in tropical regions that has enormous implications for hurricane development, water budgets, all those kinds of things. And what's important here is you're making measurements using a remote sensing technique on one part of the atmosphere, but you're putting it on a map base that gives you a geographical context for looking at this and comparing it with other data sets. Lastly, here's another example of a derived data set being put on a map base. We're looking in this case at the North Pole region, 50s and 100 years apart, projected of course in the 1950s, with ice thickness. Okay, the North Pole is an ocean, and the ice is floating. All right, so as that ice melts, sea level isn't going to change a whole lot. Think of ice cubes melting in a tumbler, nice cold iced tea, because the ice, the part of the ice below the water displaces, about the same amount of water that the ice cube weighs. At least that part below ice, that's why there's only a little bit above, you don't get a lot of changes. But you are going to have a reduced and even seasonally gone ice cover in the Arctic Ocean, and that has enormous social, economic, political, and military ramifications. There's a lot of resources in the Arctic Ocean basin, a lot of food resources. They're already setting up navigational aids for the Northwest Passage. So this is not something that isn't going to happen if we really work hard at it. It's already happening. All right. Now, let's go one more slide, please. And I mentioned, first of all, let me give an opportunity. If you have any questions on that part so far, go ahead and fire them off, and I'll respond to them. While you're doing that, if we could go to the first link on your tab. Now, there is a meta page of useful links that I'll go through with you here near the end. Some of them will lead you to places you can get more examples of what I've talked about. There are several tutorials on the fundamentals of image processing and remote sensing, but there's also a lot of places you can get classroom materials, ideas for using remote sensing tools on school projects, and we'll look at some of those. But one really good one is the Salton Sea. As I alluded to before, the Salton Sea is a large body of water. It's in Imperial Valley, California, primarily. It's not, it's between. It's just south of Indio and Palm Springs. It's well below sea level. Even the surface of the lake itself is well below sea level. And as 100 years ago, there wasn't a lake there at all. In glacial times, there was a much deeper lake, and we can still see old shoreline deposits. In fact, the wind has remobilized some of that material to create the Algodones Dunes. If you're watching TV and see a commercial for an off-road vehicle pounding some sand dunes someplace, it's almost certainly in this valley to the southeast of this on reworked old lake sediments. Around 1918, I think it was, they were starting to build irrigation canals from the Colorado River over into this valley. The soils are very dry, but they're very productive if you can get water to them. Problem was there was a big rain that winter, and the river rose and overwhelmed the canals, and the path downward was a lot steeper going through the canals than staying in the river. So all the river water decided to go downhill fast, and it ran away and eroded out these canals, and it was over a year before they could actually get control of the river again. And meanwhile, a large lake had formed. Over the next few decades, people realized that it could be pretty advantageous to have a large body of water to draw on for agricultural and recreational purposes. And after World War II, the Salton Sea boomed as a recreational agricultural resource. But there's a problem. It's a completely landlocked basin. The evaporation rates are enormous. It's in the middle of the desert. And once you cut off the Colorado River, the only water that comes into it is the rare rainfall and runoff from the agricultural activities surrounding the lake. You've got a lot of fertilizer, a lot of sediment that gets carried into the lake. The water evaporates and goes away, leaving behind an ever-increasingly salty body of water. And it has a lot of agricultural chemicals and other pollutants in it. Now you've got a real problem on your hand. It's too salty to have fish. It's too corrosive to have much of a recreational boating industry. The water requires treatment for use in agriculture, and if it continues to dry up at the rate it is, the two dates you can see there, there's been a lot of water loss over that short time period. As you expose more and more of the lake bottom, you get more and more danger because the wind can remobilize that. The lake bottom itself is a toxic waste site, and it produces a lot of undesirable air pollution. Now, if you look closely along and compare these two images, you can see that the shoreline has changed radically. What was a natural levied canal at the bottom going out, just that little red squiggle out into the lake, now is completely surrounded by a peninsula and shallow water sandbars. All up the right-hand side, there have been dramatic changes. Also, the water quality isn't as good. Notice that there's some agriculture on the lower left-hand side that's not present in the more recent image. You've lost the whole marina up in the upper right-hand corner. It's right on the edge by the right above where it says Alamo River in words. There you go. There's those dark pattern just inland. Those were inlets, and those were kind of a marina. And now, well, it's a golf course. It looks like it's completely filled in. There's a lake. Well, I suspect it's rather brackish. The reddish area above that almost certainly is a golf course. It's hard to see the distinctive pattern there, but in the original image. So the lake is shallowing dramatically, and the agriculture, again, the red in these images means strong chlorophyll growth. You get variations, of course, by the season. That's how you can tell what kind of crops are being grown. But there's whole swaths of former agricultural land that are not being utilized. These are close enough in the year. One's late May, and the other one's only a couple of weeks later in terms of season of the year. So the growing season should be comparable, and yet there's more agricultural activity going on in the older image. So this is a very powerful tool for us to monitor from a high ground perspective areas that are sometimes either hard or expensive or dangerous to reach, to look at this. At least gives us a big picture of what's going on here. There are some additional, if we go back to the slide page, that other link, there are some additional materials there. If it's age appropriate for your students to think about things on the Salton Sea, if you'll hit the second link, by searching on Salton Sea, remote sensing, or Salton Sea, ecological or environmental issues, you'll get links. This one's kind of cool. It's gives you a lot of information from the USGS about the Salton Sea, and you can actually move the cursor left or right. And there's two different images co-registered here. The purely black and white image is actually seeing out into the thermal infrared. You're seeing a heat detection. Some objects pick up and hold heat longer than others. And the other image is, I think it's visible light.
or false colored infrared. So you can see some of the reddish growth. Now they've altered it. It's not red in this one. They put the highly reflective near infrared into the green channel so that vegetation looks green. It's a little more appetizing that way than seeing, your lettuce bright red in the field. But by co-registering and comparing two divergently different data sets like this, you get a better feel for what's going on. This tactic was used on several of the Mars missions. It turns out thermal infrared will give you a clue to how coarse the objects are on the surface. If it's rocky, rocks heat up and cool down more quickly than dust and sand do. So if you have a daytime and nighttime thermal infrared picture and compare the two, you can tell which ones are dusty and which ones are rocky by how much or how little they change temperature at night. Another example would be at the beach. We're looking at a beach-type environment here, even if it is inland. Water has an enormous heat capacity. It doesn't like to change temperatures. Sand gets hot in the sun in the daytime and cools off at night. So if you're walking the beach in the daytime, you want to hop in the water from time to time to cool off your feet. But if you're walking the beach at nighttime, the water's warmer, not cooler than the surrounding sand. And remote sensing gives you a tactic to assess that over a much larger area. So there's lots and lots of information about Salton Sea in these two links. You can follow some links using this web page and follow along with that to get more information that would be age appropriate and activity appropriate for your students. Yes?
I wonder too, are there kind of like libraries of images
there are.
Teachers could use? There
are. In fact, there's some links to that on the first page, on the meta page that is available to you.
And how far back do they go? I mean, when do we start collecting this type of data?
We have in the various data sets all the way back to basically air photos, in some cases prior to World War II. There was a systematic attempt on the part of the U.S. Department of Agriculture and the Department of Interior to acquire decent photographic coverage of the entire, at least lower 48. Mm-hmm. And it's those photographs that were used to create topographic maps. So, if you go down to your map store and get a topographic map of an area, we have different techniques now, but in the not too distant past, you would use two pictures taken from aircraft as it flies along, and just like when you hold out your thumb, look at it with one eye, then look at it with the other eye, your thumb appears to jump back and forth against the background object because of the parallax angle between your eyes. The same thing's true when you're looking down from here and here. Now it's like having your eyes this far apart, and you can use 3D tactics to then determine the topography. So we have data sets, air photos, that go back 50, 60, 70 years. It wasn't until we started putting objects into space for the highest of high ground and using digital means that we got something that we could store, catalog, browse, and utilize. In fact, there's a whole family of satellites that look in all of these different wavelengths and fold in all of these other data sources. It's called the Earth Observing System, EOS, and the middle part of your meta page has the web addresses to access that information. There's the EOS main page, the EOS Data and Information System, EOSDIS, the NASA Wavelength Library. NASA Wavelength is a clearinghouse for NASA-derived educational activities. There's a whole boatload of them in there on a variety of topics. It has a whole earth science, space science segment. That would be an excellent source for these.
all of the other websites in this section. The NASA Land Science meta page will have a lot of that information. Hurricane event-based science activities, there's some pre-made ones for you. Depending on the age group that you teach, there's Echo the Bat and some other activities for younger children at NASA Space Place. We're talking now elementary or advanced elementary students. So there's some really good sources there.
That's great.
Now, I know that some of you are dealing not so much with physical geography, but rather things like urban geography, using remote sensing for land use planning, land cover analysis. There's lots of information on that in the applications of remote sensing part of the meta page that we're providing you. There's a meta page there, and if you call it up, the one that is number 2 on the geography list, SEDAC, that's one right there, that top one. And this one has a tutorial in it and some really cool stuff. If you look at this one, the second one down, the thematic guide to social science applications of remote sensing, Darren, if you'll click on the website, this has a tutorial, the second element there, thematic guide to social science applications of remote sensing, that will walk you through how the kinds of things I've been talking about find extra use in urban social science settings. Okay, it looks kind of formidable, but it's actually pretty easy reading. So I earmark that as providing a completely different perspective on this. And I haven't mentioned geographic information systems a lot because we can marry data sets of various types to a map base. The phone or the electrical power company has GPS locations for every single power pole in their system. They can see them from space. They know exactly where to send things when there's a problem. And they have a database that has when the power pole was put in, what type it is, what kind of maintenance has been done on the line in that area, all folded in. So all you have to do is click on that pole and it pops up and gives you all of that information. Do the same thing with neighborhoods. You look at how tightly the houses are packed, how big they are, what kinds of industries are nearby. You can do a lot of urban geography and sociology in a broad scale from space, and then ground truth to get calibrated as to details. I understand too that there's an interest in historical things in archaeology. There's also a segment on if we can go to the first link under to archaeology, the one that starts weather, Marshall Space Flight Center, NASA, MSFC. There you go. This is a resource you have the link to that gives a short example of various case studies where remote sensing has been very useful in triaging archaeological sites. If you're like at Chichen Itza or someplace in the jungle, the large buildings in a clearing are pretty easy to find. Finding some of the subtle overgrown roads and buried smaller structures and the small bits and pieces that can be so meaningful in an archaeological study, seeing from above can really help you out. And there is examples from Arenal in Costa Rica, the volcano observatory site there, Chaco Canyon and others. Again, heavy jungle, but seeing from above can really allow you to pick out some things. There's some links and paper references to that. So there's a tremendous amount of information accessible to you within a click or two from the meta page that we've provided. Please understand that remote sensing, image processing, and its applications is an enormously large subject. Okay, you're getting the one version here. I'm afraid. To do justice to any one of these subtopics is a semester's worth of work and a textbook or two, because these things have such powerful utility. Let me leave you with a couple of thoughts to help drive that home. The United States became a space-faring nation just after the Russians did in 1957. It's an oddity of history, okay, that Sputnik launched on the very same day that Leave It to Beaver premiered. Okay, so that kind of calibrates you as to where that happened. Okay, the United States was putting up satellites by 1959. By 1960, we'd launched our first practical meteorological satellite, and we were launching communication satellites not long after that. We knew that communication satellites would be valuable. Arthur Clarke figured that out and published on it in 1949. But having the technology to be able to implement those ideas took time. But it was so important, access to space, the utility was so high that we were using space-based platforms to look at Earth just as soon as we could put them up there with extraordinarily primitive technology. I kind of alluded to it before. Our very first spy satellite systems to go over Russia was called Corona, and it had an onboard film development capability. For those of you who can remember the old Polaroid coat, the peel, and dreadful images, that was basically the technology, photomat in space, and it would load up a reel of film in a copper kettle with a parachute and kick it out the back of the spacecraft out over deep ocean in case we missed it. We snagged it out of the air as it came down. If we missed it, we didn't want it recovered so that the other side knew what we were doing. The technology we used prior to that was to send up a hot air balloon with a camera and let it drift over. Those experiments of that technology were done outside of Alamogordo, just upwind of Roswell. We know which mission is the famous UFO mission. It wasn't a UFO. It was a spy satellite. And we let that cover story go for a long, long time. But we know the date it was launched, how far it went, what happened to it, why it looked like it had writing on it. It was kids' tape that they used to tape together a wooden framed thing with tinfoil on it so they could track it by radar without radio signals giving away the game. So the point is looking at things from above and being able to understand through the big 8 elements of image interpretation and the colors involved, determine what you're looking at, has been an enormously powerful thing and will continue to be. As our technology gets better, we will have refined tools, but we'll still be using those tools on the same tasks. If you have any other questions, I'll be glad to answer them from here on the side. I hope you've enjoyed our time together. I certainly have, and I look forward perhaps to spending some time with you in the future on this kind of thing. Here's some additional geography archaeological things. I'm given to understand that you'll have access to the PowerPoint after the show, so don't wear your pencil out writing furiously on this one. Between that and the meta page that we provided you, I hope that you can augment your classes and your students will enjoy having a new twist to work with.
Absolutely. Well, thank you so much, Stephen. What I liked most about this was the idea that a lot of inquiries could support a lot of different disciplines using this type of data, and also kind of putting students in the role of to kind of think like decision makers, whether it be political or militarily, or even just forecasting what might happen in the future based on kind of change over time, especially with the environment and human impact. As Stephen mentioned, we have a Learning Lab collection. So if you're not familiar with the Learning Lab, that's at learninglab.si.edu. And I've created a series of links, including some sample images, as well as Stephen's recommended list, including some of the links to how to interpret an image, as well as some galleries so that you can kind of take a peek and see some great examples that you could use with your students starting tomorrow if you'd like. Wanted to thank Stephen for his participation in this session, as well as all of our participants. You can access the archive here on our Google Plus page or on the Smithsonian Education YouTube page. You can also take a peek at our Learning Lab collection. It's published, so feel free to search through and take a peek at some of the resources we've provided for you to continue your exploration in this topic. And finally, on the Learning Lab, you can actually adapt pre-made collections to tailor them to your students' needs and to create your own from scratch, so if you'd like to do that as well. We hope you'll continue to join us for our last session in this series for social studies educators. The next session will be with two of my colleagues from the Freer-Sackler Galleries. They're going to be making connections between archaeology and the study of ancient China, so you won't want to miss that. That'll be on Tuesday, April 12th at 4 p.m. And thanks again for your participation, and we look forward to seeing you soon.